The challenge of this problem is that we are given derivatives with respect to time for what happens in the x position, the x along the x direction of a particle's position, and then separate from that, what the y component of that particle's position is doing. In this problem, we're talking about the position of a particle and how it changes over time. What makes it more challenging is that we're given the position of the x-coordinate with respect to time, as well as the position of the y-coordinate with respect to time. We have to deal with both of those simultaneously. So these are the two formula that govern what happens to the x-coordinate as a function of time. This is the rate of change of the x-coordinate. And this is the rate of change of the y-coordinate. That's valid for all positive times. We're also given an initial condition. When time is 3, the x-coordinate is 5, and the y-coordinate is 4. So part A asks us to find the speed of the particle. Well, we know that the speed equals the absolute value of the velocity. And they want the speed of the particle at t equals 3. So that's the absolute value of the velocity of the particle at t equals 3. So first, let's find the velocity. Well, the velocity has an x-coordinate and a y-coordinate. And so at t equals 3, the velocity is going to be 6 over 3 minus 3 to the 1/3. And that equals -1. And we also, so that's the x-coordinate. And the y-coordinate of velocity is going to be 3e to the -t. And that comes out to be approximately 0.14936. So, given that we know the x-coordinate of the velocity and the y-coordinate of the velocity, how do we now find the speed? Well, here it's important to remember that the absolute value of a vector is the square root of the individual components squared and summed. And so it's the square root of -1 squared plus that 0.14936 squared. And that comes out to approximately 1.01109. Let's see what B has in store for us. We have to write an equation of the tangent line when the particle is at time t equals 3. Here again, it's important that we have a correct overall understanding of the setting. If these are the x and y coordinates, then the particle itself moves as a function of time and gradually sketches out some path. And let's say right here represents t equals 3. We've been asked to find in the xy plane that tangent line. Well, finding a tangent line, as we know from a great deal of experience, has to do with knowing the point of tangency we have the point. The point is 5, 4. And it also requires us to know the slope. But the slope in the xy plane means finding dy dx. Whereas what we have is dy of t and dx of t. Well, it's fairly straightforward to see that dy dx is dy dt divided by dx dt. And that comes out to negative 0.14309. So now we can write our line as y minus 4 equals negative 0.14309 times x minus 5, using the simple point slope formula that at this point we're all quite familiar with. Might even say a bit tired with. But that's neither here nor there. So let's go on to part C. When is the particle farthest to the right? Well, farthest to the right is talking about a global extremum. In this case, a global maximum of the x coordinate. So we're saying at what time is x of t a maximum? Well, we know how to find global maxima. We consider the endpoints. And we also consider the any place where dx dt changes from positive to negative. Well, what about the endpoints? Well, the endpoint presumably is 0 for time and infinity for time. However, since neither of those are reachable, then because they're not in, neither t equals 0 is included in the domain, and we can't actually reach t equals infinity, then those are not our points for checking. Instead, we need to look for that point where the dx dt, the change of x with respect to time, shifts from positive to negative. That's fairly easy to identify because we have the formula for dx dt, and where the cube root of this changes from positive to negative is the same as where this quantity itself, 6 over t minus 3, changes from positive to negative. So where does this change from plus to minus as we go left to right? And the answer for that is pretty clear. We see that it occurs when t equals 2. So let's see if we can't conclude from that how to deal with this. We want to find out what value x has when t equals 2. Well, we have its initial value at 3. Okay? So what we really want is x of 3 plus the integral of x from 3 to, rather the integral of dx dt from 3 to 2. We can evaluate that numerically. And we get 5 plus a certain additional amount that comes out to 5.79156. Notice that we don't have to start out in our integral at t equals 0. We call t equals 3 the initial condition because that's where they give us the values. We can always start from that number and go either forward or backward in time or whatever else our variable of integration is to arrive at the value at some other point for that variable, in this case time. So the idea of integrating backwards from 3 to 2 shouldn't pose an issue for us conceptually. Again, why did we ignore the 0 and infinity possibilities? Well, another way to think about it is, as I said, we could never reach 0, but we don't really want to because we can see that once t is 2, that things keep on progressing in a negative direction, so the x is moving backwards from that point on. And so it's really only from 3 to 2 that it makes sense to be integrating. Okay, that leaves not a lot of room, but let's see if we can't fit in part D here. So what is the behavior of the path of the particle as t increases without bound? Well, first, what is the dx dt behavior? Tell us. Dx dt, it says as t increases without bound. That's really just asking us to understand what's the limit as t goes toward infinity of dx dt. And what we see is that is a quantity that continues to be negative and finally is going to be roughly -3, right? That limit, in that limit, this 6 over infinity will go to 0. And so the limit is, really don't have room to write this here, but I'll put it anyway, -3 to the 1/3. So it continues moving to the left. Now, what about the height? What happens to dy dt? Well, that is te to the -t, or in other words, t over e to the t. And what we understand about the rate of growth of e to the t compared to t is that this grows much faster, the denominator, and therefore t over e to the t is going to go to 0. So it continues to the left and it plateaus with respect to its height, reaches an asymptote in height. Again, what makes this problem challenging is being able to keep straight in your mind what is happening to the x-coordinate versus what is happening to the y-coordinate. It was only in a couple of places where we had to combine what was happening with the x and the y, here in this instance for speed, and here in this instance to find dy dx.